talking about density function theory. You remember? Okay, so our goal is to avoid dealing with many body, many fermion wave functions. Okay, and this is why we have this DFT, which is density based, and we are trying to look only at the density. And what we have established in the last lesson was that, in fact, if you are interested only in the ground state of a non-degenerate system, then, in principle, everything, all ground state properties, and in particular its energy, are determined by the knowledge of only the density. And I've argued that the density is a much simpler quantity than a many-body wave function, because it's simply a scalar, it's a number at every point in space. Okay, something you can very easily represent in a computer, you can deal with it. It's just a non-negative number, and it must integrate to the total number of electrons. So something very easy. And now we have, I'm not only telling you, but we have proven mathematically that, in fact, there is a one-to-one correspondence between what is the fingerprint of your system, the external potential, and the density. Okay? So we have shown that you cannot have two different potentials and the same density. Therefore, if you have a density, there is always this one-to-one correspondence. What we have not proven is, in fact, that for a given density, you always can find a potential which leads to this density. But this is something which is, for if the density is well behaved, it is always, one calls this V representable, so representable by potential. So there's really, for us, for all practical purposes, this one-to-one correspondence. So since all properties are determined by the density, now today's goal is to find out how can we find out what the energy in fact is if someone gives us a density. Okay? So within density function theory, therefore, what we do today is the so-called Coulomb approach. Coulomb formalism, which comes from a paper published in 1965. Okay, so the cone is the same cone of the Hohenberg and Kohn theorem, which we have proven 2 days ago. Okay, so since we know that the density can be taken as our key quantity, we know that something like this exists. So we know that there is a functional of n. Okay, so this is not something where you have just a number, but you put in a whole function. In our case, the function n of r, with all its shape it has over space. And this functional for the shape of n gives you back an energy, the energy of the ground state. Okay? So now, unfortunately, the theorem we have seen last time, it gives us no clue whatsoever and no indication of how this looks like. Okay? So what shall we do? Any ideas? Any suggestions? What could we do? We know that this thing exists, but we do not know how it looks. And we would obviously like to write down something, some energy. Well, one of the kind of a good idea might be to think about what we already know about the many electron system. We have already, for example, done Hartree-Fock. Okay? And remember, in Hartree-Fock there were different contributions to the energy of an interacting electronic system. No? So we could now think, okay, we do not know its exact shape, but we can probably already say what will be ingredients to this energy. Okay? For example, one ingredient will be the interaction with the external potential. No? So there will be an external potential, atoms which act on there. We know the density, and very certainly this will lead to a contribution to the energy, which is the potential times the density integrated over space. This is something which appeared in Hartree-Fock, and it will certainly be there. An electrostatic interaction of this with the external potential. Another ingredient which will certainly be there is if you have charges here and there and so on, one part of the energy will certainly be the classical Coulomb interaction between charges here and there. So 1 over r interaction between the density here and there. You remember the Hartree part in Hartree-Fock was precisely this. And it was written simply as n of r1 times n of r2 divided by the distance and integrated over r1 and r2. Okay? That was a prototype of a functional of n, and certainly something like this will appear in the energy. Another contribution. What might be another contribution to the energy? Well, you seem all asleep. In Hartree Fock, what was also there in the energy?
Self-interaction.
No, so if you write this Hartree term, then if it's just for one electron, yes, it would self-interact, and that is not good. But there is a term which certainly will need to be modeled somehow. In Hartree Fock, what did we have? We have Hartree, we have Fock, we have the external energy, and we have kinetic energy. So certainly a quantum system of electrons will have some kinetic energy. No? We do not know what it is, but certainly it will be there. So our idea is, we do not know what this is, but we know certain ingredients which will certainly be important contributions to it. So one of them will be some kind of a many-body kinetic energy, which we try to write as a function of n. Okay? We will certainly have something which looks like the Hartree energy. So we will have some Hartree energy as a functional of n. Okay? We will certainly have some external energy, which is the interaction with the external potential as a function of n. Okay? So these things will certainly be there. We do not know how to write this yet. We'll talk about it later. We know how to write this, because this here, the Hartree energy is simply double integral over dr1, dr2, n at r1 times n at r2 divided by r1 minus r2. So this here, you see this here is a functional of n, because you need to know the function n to calculate this double integral. But once you have n as given, then you can simply calculate the Hartree. So this is a prototype of a functional of n, and certainly this term here will be somehow part of the energy. Okay? The external one we can also already write it, because we know where our atoms are, and the electronic part, this here will then simply be integral d3r of n of r times vx of r. Okay. So also this here is a prototype of a functional. You give me the functional n of r. This is given because we know where the atoms are, what kind of atoms. So we have this thing here, and we can write this. So this we have written as a functional of the density. This we have written as a function of the density. This not. But we cannot just stop here. If this was Hartree Fock, we knew kinetic energy, Hartree external. We would also have. What would be missing if this was Hartree Fock? Who says? The Fock term, the exchange term would be missing. So this is missing. And then, I mean, we do not aim at getting only Hartree Fock energy. We want to do better. We want to get the exact energy. So it's also missing is all the correlation energy. So if you write it like this here, okay, we have two terms we've already identified. This we will have to deal somehow with, but we know what the kinetic energy is. But certainly something is missing, written like this. Okay? And this what is missing, let us just write it down as another functional of the density. We know that it must be a function of the density, and it is everything which is missing in these parts. And since one thinks about Hartree Fock, what is missing precisely is exchange energy and correlation energy. Okay? So this term here is in density function theory. This is the famous exchange correlation function. It's a complicated word because people like fancy names. Okay? So exchange correlation, it sounds very sophisticated, but what it really is and where it comes from is by saying we have identified certain terms in the total energy, but we know that this cannot be all, so something is missing, and the missing rest we call it exchange correlation. So exchange correlation is a complicated name, but the true word or the name we should be given to it is the missing rest energy. Okay, so it is everything we have not yet included here, and you can imagine this will be something quite complicated. So we do not know what it is. The famous scientist Feynman, of whom you have certainly heard already many things, who were always saying funny things, he also said this should not be called exchange correlation energy. He said this should be called stupidity energy, because we humans, we are too stupid to write down what it is exactly. Okay? So everything which is missing, which we cannot identify clearly as a kinetic energy, as a Coulomb interaction, we are too stupid to write it down. So this should not be called exchange correlation, but should be called the stupidity energy. Okay. So you see there are many energies, but if you want to sound serious and you go to a conference and show your results, you should call it, like everyone does, the exchange correlation energy. Yeah? And I can already tell you that, so in DFT, having a form for this here is the main problem. Okay, so obviously, because all difficulty, all the correlation stuff, and you already got the feeling from the correlation is something very complicated, because you need many determinants. You need, if you do it with a configuration direction and wave functions, you need to do something really complicated to get correlations. And now, to get the correlation out of knowing only the density, it's really difficult. So this here is really the part which makes us headaches. We will be talking about how one approximates it, but so this is where all approximation, most of the approximations go. Okay. So this is the unknown thing. This here we know exactly what it is. This we know exactly what it is. I've already written it down. And this is the second of our problems. Okay. So we now have, at least per forma, written down a functional of the density, which gives us the DFT ground state energy for a given density. Okay. So imagine that we knew now the exact form of all this, so that we had a term written down like this also for here and here. Imagine we had it. Okay. Then what we would need to do is very simple. What we need to do is to minimize this expression with respect to n. Okay. Then we find, for a given system, which is defined by a given external potential, we find that density which minimizes the energy, and therefore this is the ground state density, and we find the ground state energy. Okay? So this here, once we have an expression like this here we minimize. With respect to n of r, and we obtain E of n min is the E ground state of DFT. So this is what we need. So we are left, before we can minimize something, we have to solve two problems. One small and one big. Okay. You can take this away. The small problem is we have to find a way to write the kinetic energy as a function of the density. Okay. So it's a problem, but it's not an unsurmountable problem. And we have to find something for this. This is nearly unsurmountable. This is the real big trouble we have. Okay, but so we have two challenges to overcome in our lesson today. Okay. So if I write this in a little bit different order, we have kinetic energy, we have R3, we have exchange correlation. So I just change the order and leave E external. So the interesting thing is, you see, what of these energies depends on the system you're looking at. Again, if you're looking at 4 hydrogen atoms with respect to a beryllium atom or a lithium and a hydrogen atom, they are all systems with 4 electrons or 2 heliums. So what makes a difference between them is only this part here. This is again the fingerprint of your system. Okay? This is what distinguishes one system from the other. If you want to find out what is between 2 helium atoms, what is the equilibrium distance? Okay? Only this here changes if you change the distance. Only this is system specific. And these here, you see here, there is no relevance. This is a kinetic energy, heart rate, and exchange correlation. These are things which do not depend if you are in a carbon, or if you are in oxygen, or if you are in a transition metal. These are completely general things. So this is why the sum of these three here, this is sometimes called f of n, and it is a universal function.
So we know that ext depends upon the system because we know its form, we know how it
Exactly.
works.
I mean, I had written down
But
before.
how do we know that extends something that we don't know is independent of the system?
Well, because we know that it is a function of n only, and therefore, I mean, n will be different from going from one system to the other. But if I give you an n, all these energies which you have, they must depend only on n.
But
I mean, exchange correlation, so, and like the kinetic energy, like all this, it cannot depend on where the external potential is acting on your atom. This must really be something where the knowledge of n is enough to know what it is.
But the first two I understand. It is, and the last one also it's fine because there is like r, the coordinates of the atom, and
Exactly.
the j, the number of
exactly.
neutrons. But in a simple system, we don't know the form of E extends correlation. If we had known, we wouldn't have this problem in the first place. This is something unknown.
Yeah,
so how can we say that it doesn't depend upon nucleus? Because we say that this depends upon doesn't depend and this depends because we know its form in the purest purest system.
Yes.
But we don't know anything about the E extends.
Yes, we do, because remember this graph we have been drawing last time. Okay, so if we would solve the real problem, okay, then you would start from having the external potential. You put this into the many-body Schrödinger equation, and the only term in the energy where something is system-specific is precisely with this Vx. All the rest is independent. And this is then reflected in this term here too. So this is really, I mean, Hohenberg and Cohn, that boils down to having to find something which is completely system independent and universal as a function only of n, in the same way as this and this term here is. And only here we have something which is dependent on the system. So we know this from how one would proceed in a procedural way by solving the many-body equations. Okay? There you see in the many-body Schrödinger equation, which clearly is one way to solve it, that the only part where the energy where the system-specific things go in is in this thing here. And therefore also in density functional theory, it can only be reflected in this here, the system-specific function. So the sum of these three, we do not know yet its exact form, but we know that it must be universal. But this here is system-specific. So now that we have kind of written down little pieces, let's attack one problem after the other. Let's start with the kinetic energy. So, when we think about kinetic energy in a wave function way, in Hartree-Fock, remember we had kinetic energy, we never had to think about it, because in Hartree-Fock it was simply the sum over all orbitals we had, and for each orbital we had h bar squared divided by 2n with the minus sign of psi I, second derivative psi I. Huh? That was it. These are single particle orbitals. We derive them twice, and we make the sum of all occupied orbitals, and that was kinetic energy. So, this we cannot do now, because unfortunately here one has to derive an orbital, and the density is already a sum over all orbitals, their modulus squared. So while in Hartree-Fock it was a no-brainer, now writing t as a function of n is not so straightforward. Any suggestions what we could do? How can we write t of n? Even if it's only in an approximate way. And remember, the people who first had to solve and think about this question were Coulomb and Cham in 1965. So imagine you know all physics invented up to 1965. What would be the first thing which comes to your mind? You were not born yet in 1965, you can argue, okay? I'm quite sure all of you have already heard about something in this context.
How about gradient of n?
Gradient of n might appear, but no. If you turn around yourself, you see a building up there. Fermi building. Something which carries Fermi's name. Well, these are fermions, obviously. Electrons are fermions, so no, but no, it's not Fermi-Dirac, it's something with Fermi. Never heard about Thomas Fermi?
Thomas Fermi.
And it is not that his first name is obviously Enrico Fermi. No, Thomas is another scientist. Okay. So one possibility which certainly Coulomb and Cham immediately thought about, well, we need to write the kinetic energy approximately with the density, and this is something which has already been done in when was it? Wait a minute. This was already in 1927. So really in the years where quantum mechanics was invented, one could say we use the Thomas Fermi approximation, and it's very old, it's 1927. And the Thomas Fermi looks like the following. It is a lot of constants which never anyone remembers. It's 3h bar divided by 40 times the mass of an electron, 3 divided by pi to the power 2/3, integral of the density to the power 5/3 over all space. Okay, so this is something we can very easily calculate, because if someone gives us n of r, we only have to take it to the power 5/3 and integrate this over all space. This again is a typical case of a functional. You get a function and you integrate and you get out a number. So here you have what you want. You have written something which is a kinetic energy, written as a functional of the density. Now where does this come from? Certainly it is not very complicated quantum mechanics, because they invented, these were two genius people, okay, but in 1927 when not so much about quantum mechanics was known yet. So they were thinking about atoms, okay? And then they said, well, the kinetic energy of an electron is p square over 2m, kind of what we also would like to write, okay? And then they were integrating in momentum space p square over 2m up to the modulus of p being what they called the Fermi value, or the highest value of p, which might be occupied. And then they were simply saying, if we know what the density is, we know up to which p this will be occupied. So it's 2-3 lines of calculations. And they, in this very easy way, ended up by integrating p squared over 2m times what they assume to be the density in momentum space of electrons, such that if you integrate them, you get n of r, and then you end up with an expression like this. If you look in the internet, Thomas Fermi theory for kinetic energy, for example, even in Wikipedia, you find something, it's 2-3 lines. It's really very easy. It's just hand-waving arguments of how in an atom, if everything is isotropic and so on, you get kinetic energy for density. Okay? So it's something which has certainly been known even in the distant 1965. This was already an old result. So certainly this is something which Coulomb and Cham thought about immediately. A little bit later, this has even been improved. So that is also, so if this should not be good enough, one can write a correction to it. To Thomas Fami. This comes from a scientist whose name is von Weizsäcker. Probably you need to be German to pronounce this correctly. Von Weizsäcker. His nephew was for many years president of the German Republic. So this is one of the kind of the Kennedy family in Germany. Everyone knows them. So, and this guy von Weizsäcker, he has made a correction which one could add if one wants to this. So the von Weizsäcker kinetic energy term is 1/8 h bar squared divided by m, and then he also added the gradient of the density squared divided by n of r, and you integrate also this over all space. Also, this is a typical example of a functional. Someone gives you a function n of r. You can calculate at every point in space its gradient. You take the norm square of the gradient. You take this and you integrate this over all space, and you get out a number. Okay? You multiply it with some constant. So this is again a functional of the density, which in this case even includes the gradient of the density. So one can take for this term here Thomas Fermi and add, for example, if you want to do something better, the von Weizsäcker correction to it. I don't remember who of you said before a gradient of the density. You? I don't remember. Okay, so you see, in fact, that gradient at PS is not so surprising because the density is psi star times psi, okay? And the kinetic energy is the second derivative which should be in there. So if you take a gradient of the density, it is not so surprising that something like this might appear in an expression for the kinetic energy. Okay, so it seems that when DFT was formulated and the Coulomb approach was made in 1965, when was this here? Let me also say, this was in 1935. So even that was already a very old result at that time. So nothing fancy for these people and so on. So it seems when one needs to write down a density functional, the kinetic energies are under control because we have some well-known expressions which we can use. This is the good news. The bad news is that it does not work at all. Okay? So we know these approximations here, but it became very quickly very clear to Chang that this is not usable. Unfortunately. So not good enough. In fact, you can, if you try it today, you can very easily, we have some, obviously today, some expression for this exchange correlation. If you use our expressions for exchange correlation, and you plug in here Thomas Fermi or Thomas Fermi plus von Weizsäcker, and you minimize it, I mean, all this is there, you will find that you do not get the right chemical bonds, the right chemical properties. It's not a useful theory. This is not good enough for being used really as an alternative to Hartree-Fock and correlation and wave function methods. So, and this they already realized in 1964, Coulomb and Chang. They said we need something else. Okay? So, this is a typical case where one is looking for something, the expression for kinetic energy as a functional of n, where a solution seems to exist already even since more than 30 years, but it's not usable. Okay? So, this is nice, but not good enough. So, now we are left with something, we are kind of at square one again. We need an expression for the kinetic energy. We know how it would look in Hartree-Fock. We would like to have it as a function of the density, but what is available is not good. So, what did Coulomb and Chang do? They said, let us do a change of variables. Okay? We know that in DFT, we have proven it ourselves that the density is the basic variable. But we would like to be able to write something which is the sum over orbitals where you have orbital complex conjugate, second derivative of the orbital. This is what we would really like because we know this leads to good approximations for the kinetic energy. So they said, let us introduce new variables. And now comes something which, when you hear it for the first time, it seems to defy the logic of density function theory. Because they say, okay, n of r is our basic quantity. But we now reintroduce single particle orbitals, as if we were looking for a wave function. So what they say is, we introduce new variables which are such that we have n of them, and the sum over all of them is phi I of r complex conjugate phi I of r. So we do as if we were in a wave function theory, kind of like in Hartree-Fock. We say the density, we write it as the modulus squared of some single particle orbitals, and we take n of them. And they say they require those phi I to be orthonormal, like it is in kind of Hartree-Fock. Now it seems that I'm on a path to go back to wave functions. No? It seems. But this is not at all what they were doing. So Cohn and Sham, they said, we write our density like this, but we remain within density function theory. So at no point it is claimed that these orbitals, in fact, very often this is with psi ks. So these orbitals are referred to as the so-called Cohn-Sham orbitals. I will in the following not always write it, but keep in mind these are Cohn-Sham orbitals. These are not the spin orbitals of a wave function theory. So Cohn-Sham orbitals. And they are very often referred to either as Cohn-Sham orbitals or as, and now comes the keyword, fictitious orbitals. Fictitious means something which is not really real. Okay? So, why are they fictitious? Because in this whole approach, in density functional theory, one is never ever claiming that the many-body wave function is made out of a determinant or many determinants or something which makes intervene these orbitals. These orbitals, you can see it as auxiliary variables. As if you, so, and in fact they are a mathematical construct, one introduces to write the density as a square of their moduli. Okay? And they are not meant to represent in any way the many-body wave function. They are only meant to represent the density via their moduli. And why did they introduce them? Well, they introduced them because then, now they say, we use as an approximation for the kinetic energy, and this is often written Ts of n, an approximation for the kinetic energy, which we are looking at. This here is written as the kinetic energy of these fictitious Cohn-Sham orbitals, by I Cohn-Sham. And it is what you would expect, the sum of h bar square over 2m phi I Cohn-Sham second derivative phi I. So now this here we have an approximation for the kinetic energy, which looks like what you have in Hartree-Fock, but it is not written with orbitals which are supposed to represent a determinant or many determinants or whatever. It is written in terms of auxiliary variables which look like a wave function and whose square is the sum is the density we are talking about. So the price you pay by this thing is very high, because here you have only one easy quantity, which is a scalar everywhere in space, a non-negative scalar everywhere in space, the density. If you make this change of variable, and you take as basic variables now these Coulomb orbitals, rather than the thing, then you have n of these things, which you have to keep orthonormal, moreover. Okay? So all the formalism becomes more involved. But this is the thing which made the success of DFT, or one of the ingredients of DFT. Because this approximation of the kinetic energy, this TS, is a very good approximation. Okay? So later, imagine you have some approximation for this. Now we can minimize everything. We minimize these terms here. We minimize with respect to n, and then chain rule, we derive n with respect to phi. Okay? This here, we replace t by this approximation Ts, and we derive it directly with respect to phi. And then we have an expression which we can minimize, written as a function of these, which we keep orthonormal. Okay? So we will obtain an expression which looks like something acting on orbitals, but the nice thing is we never have to treat a determinant or anything like this. These orbitals really, they appear only because we want to change from this basic variable to this and have this approximation for the energy. It's really the kinetic energy which is the problem. Yes?
Maybe I did not get it clear, but as if I heard you saying that we minimize EH, EXT, and the exchange correlation energy with respect to n.
Yes.
And
So, in principle, we have to derive with respect to n. But we will have here the approximation Ts, which is written as the term in terms of these.
so then it becomes something with variables.
Exactly. So, in fact, this here becomes a functional of the Coulomb orbitals. Okay. In the Coulomb approach, the energy function is a functional of the orbitals. Because these terms here, which are functions of n, we know that n is in fact n of these orbitals here. Because if you know the orbitals, you know the density. Okay? So wait a minute. So if you have to derive, so this here is a function of n, but n itself is a functional of the phi's in this sense. Okay? So if you have to find the minimum of this here, this means now you have to find the minimum with respect to the phi's. Okay? Here, in this expression, for example, this you have written explicitly only in terms of n. But this is not a problem because n is a functional of the phi's. So the chain rule tells you, in order to find the minimum of this term with respect to the phi's, you calculate dE with respect to dn and then dn with respect to d phi. Chain rule of derivations. Okay?
Yes.
This is what I mean with chain rule. So these terms which depend explicitly only on n and not on the orbitals, you derive them with respect to the orbitals by deriving with respect to n and then dn over d phi, which is trivial. Okay? So we will have, the Coulomb approach leads us to having the energy as a function of n, but written as the energy as a functional of fictitious orbitals. Still, we have not done anything wrong, okay? I mean, if we have a good approximation for this, then we have, in fact, we are still in the region of an exact approach. Yes?
But if we are to minimize with respect to n, I expected that all these three terms, the Hartree fork, and then the external potential, and then the exchange whatever, are all going to give different values of n minimizing them. So what are you going to do?
Yeah, wait a minute. So you have a sum, you're minimizing the sum. You're not minimizing separately this and then separately this and separately this. No. You're minimizing a sum.
The sum.
Yes.
Minimizing-
As always. I mean, if you have a function h of x, which is f of x plus g of x, and you minimize this here with respect to x, The minimum is not the minimum of this or the minimum of that. No, the minimum, the x which minimizes the sum, depends on f and g at the same time. Okay, so we are not minimizing. We are minimizing this here with respect to the phi's. Which terms appear? The derivative of this plus the derivative of this plus the derivative of this plus the derivative of this. Like if you minimize a function h, okay, you minimize h with respect to x, and the derivative is the derivative of f plus the derivative of g.
So this is what
so here you will have the derivative of this plus this plus this plus this.
This is what I don't understand.
Yes.
You have said we first minimize the last three terms, we get n, and then we use that.
No. Then then you misunderstood, or perhaps I said it wrongly. Okay, so we need to minimize this,
Yes.
but written as a functional of the phi's. For this we need a derivative. We need the derivative of e with respect to phi. Okay, so we need to get the derivative of all of these terms with respect to phi.
This one's also known in terms of phi.
Yes, and they are known in terms of phi because they are known in terms of n, and n is a function of phi. Okay, so you have e of n, but this is in fact e of n, which depends in turn on the phi. Okay, because it depends in this way on the phi's. Okay, so now the derivative of e with respect to the phi's is the derivative of e with respect to n times the derivative of n with respect to phi. This is what I'm saying. Okay, and obviously there's a term corresponding to this, a term corresponding to this, a term corresponding to this, and a term corresponding to this in this derivative. Like here, if you derive h, you have a term, the derivative of this plus the derivative of this. Yeah, perhaps I've expressed myself wrongly. I'm not saying that we derive these and get an n and then we plug it in. No. We have to have a derivative, which then we say the derivative is 0 to get the minimum. Okay? So if we derive this term here with respect to the phi's, here we will get directly the second derivative acting on phi. Here we will get the Hartree energy derived by n, and then n derived by phi, which will give us a phi, and so on. I mean, we'll write the equation later explicitly.
But earlier on said that there is some energy for which we don't know how to write explicitly.
Yes, this one here. This is the next thing.
How do you?
Yeah. I mean, this. So there are two issues we need to do. First, we need to find an expression for n, an approximate expression for the energy. Okay. Once we have this, then the next task is to minimize it. So the minimization, we can really talk about it once we have explicit forms of all of them. Okay. And I said we have to solve two problems today. One is a kind of a more easy task, which is finding an expression for this. The very difficult task is this. So we still need to find an expression for the energy. The only thing we now know, in order to get a good approximation for the kinetic energy, we have to go one step further and write everything not as a function only of the density, but of fictitious orbitals. They are fictitious because they are not supposed to be part of a determinant making a many-body wave function. We do not talk about many-body wave functions. Okay? You can see purely mathematically as a change of variables. Instead of this variable, you talk in terms of this variable, and the two are linked.
Excuse me, sir. About
Yes.
the structure of this orbital, since we are in the same Hilbert space, they are spanned by
In the same Hilbert space as?
Okay, for example, if we started from, let's say, the Hartree fork,
Yes.
so we assume some basis, and then we made these spin orbitals by expanding it, and then we started taking either this or this, and we put the determinants. So I think the dimension is same because like we have any
Yeah.
electrons.
Later in a computer, when we need to represent these orbitals in the computer, again, they will be written as linear combinations of basis functions.
Of the
Yes.
same basis function. So why are
The
we
same, yeah,
calling it-
people use for Hartree-Fock sometimes different basis
Yeah,
functions. than
but
for
still,
density.
the structure is same. It's
Yeah,
orthogonal.
you will find something, in the end we will end up with, in DFT with equations which look very similar to Hartree-Fock. And this is why one needs to be very careful about what is the difference between Hartree-Fock and DFT. I will insist a lot on this difference. Yeah, we will find something, you're completely right. We will end up with something which formally looks a lot like Hartree-Fock, but which is completely different from Hartree-Fock.
But wouldn't it be wrong to call it fictitious because these have all the these are generated by the same basis. These have all the
No, they are
structures?
they are fictitious because you see in Hartree-Fock you clearly approximate your many-body wave function, and you approximate by saying it's a single determinant and so on. So there they are really elements of an approximation to the many-body wave function in Hartree-Fock. Here we are not approximating the many-body wave function. So, for example, what we get out will not be a variational approximation to your energy. This is a big difference. Okay. In DFT, we are not trying to approximate the many-body wave function. Therefore, we have no guarantee that the energy we get will be an upper bound to the energy. And in fact, you might remember I've shown you some DFT results. Often they lie below the real result. Good. So we are now at the point that we have an expression, thanks to this change of variable, for the kinetic energy. I've been very careful at writing this always as TS. S is shortened for single. Okay? So because it's written in terms of these single particle fictitious orbitals in this way, as it's written here. Now, obviously, it is an approximation. Okay? The real many-body kinetic energy, which you can write down, if you know the exact wave function, you can write down the expectation value of the kinetic energy operator in your Hamiltonian. This is would be the kinetic energy. This would be T. Okay? We approximate it by something which is written in terms of fictitious orbitals. So we approximate T with Ts. Okay? And this is something which typically works very well, but it's an approximation. While this here is all exact so far. Okay? So now since we approximate this first term here with something which might be a good approximation, but we approximate it, this means in our rest energy, in the rest with meaning the difference between the exact result and what is before, there is not only exchange, there is not only correlation, there's also something which accounts for the difference between T and Ts. So just keep this in mind. Many people forget this because it's always called exchange correlation. People always think, this has to account for exchange and correlation effects. No, it has also to account for the difference between the true kinetic energy and the one we approximate in the Coulomb formalism with these orbitals. It was, I think, 2 or 3 years ago, we had an introductory school on density functional theory here. And the speaker was a guy who has founded a company. So he's an entrepreneur. I don't know if he's also rich, but he is selling computer programs which can do, amongst other things, density functional theory. Okay? So he was giving a kind of introduction of this kind, and at a certain point he said, "Yeah, be careful that there is this difference. This is only an approximation. So therefore, exchange correlation contains, in order to remain exact, also this difference." And then he said something funny. He said, when he is hiring in his company new collaborators, obviously there's an interview for being hired, where he tests if the people know DFT and they know their physics. And the thing which he always asks is, what exactly does exchange correlation have to care? And if someone only mentions exchange and correlation and does not mention this, then the person does not get the job. Okay, so if ever you apply, now it's public, so I cannot tell you the name of the company, but if in the future you decide to apply for a job in a private company which does DFT codes, then ask me, I can tell you, be careful. Always mention this. Okay? So exchange correlation is our stupidity energy. It must contain, because in principle DFT, as I underlined many times, is an exact theory. So this is the exact ground state. We write it as a sum, and all we do not know, it must be here. Since here now we are working, I mean, Hartree and external, we have written it down, whatever it is. This here now we approximate it. However good the approximation might be, it is an approximation, and the difference is also here. So what we have done so far today is we have written down the function which we know what it is. We said there are two problems, kinetic energy and exchange correlation energy. And we have found an expression at the price of introducing again single particle orbitals. So we have to pay this price, but thanks to this price we have a good approximation. I can already tell you it's a good approximation for this here. And now we are left with the real tough part. The real tough part is we have in some way to find an expression for this. And this will be really difficult. So, and I think the real power of Cohn and Sham and of this 1965 paper was that even at the time where they had very limited computers to do things, they have already understood many things. They understood they cannot use Thomas Fermi even with the von Weizsäcker corrected for the kinetic energy. They had the idea of replacing that kinetic energy with fictitious orbitals, which is, I find, already a good idea. But then they even suggested, even though they did not have the final form of it, they even suggested how one can approximate this. And I'm quite sure that DFT and this whole Cohn and Cohn and Sham, it would all have been forgotten, if not, and they could not know this when they published it, if their first suggestion of how to approximate this here did not work really, really surprisingly well. Okay, so I mean they suggested it, people were not paying much attention also because computers were not good, but then with the years when computers became better, people started trying out their idea. I don't know, why does this work so well? And then, I mean, once something works well, then people get interested, and then a lot of other research was done. But in the first attempt where they suggested their idea, would not have come up with some suggestion of what one could do here, I think it would have probably been forgotten. Okay? But it was not forgotten, and now we have to find our way of approximating exchange correlation. So we need to know what could be E exchange correlation as a function of n. We know the ingredients, and we know it will be kind of difficult to write. Now, once that we have decided that we introduce these single particle orbitals for reason of the kinetic energy, we could say, if we have these single particle orbitals, we can at least the exchange part, we could also write it in terms of these orbitals. No? Because in Hartree-Fock we know what it is. You remember it is psi I times psi j at a position r. Then at another position it's again psi j times I divided by the distance. This is what it is in Hartree-Fock. Once you have single particle orbitals, you could take this thing, and this is something which is known as exact exchange. We will talk about this later, but this is not at all the approach which they have followed, luckily, because that would have led probably to a dead end. Trying to write for exchange the Hartree-Fock expression. Why would it have been a bad idea? Because you have exchange and correlation. And you remember how correlation is defined. It is defined as the difference between the exact result and the Hartree-Fock result. So in order to have a handle on correlation, writing it down in terms of wave function is something very, very complicated, because you do not get away with dealing with a many-body wave function. This is precisely what you do not want to do in DFT. Okay? So if you start approximating this term here by writing, again, putting it in pieces and writing the exchange here, then you are left with having also to write the correlation part exactly, and that is intrinsically a wave function thing which you cannot do easily. So at that time, they did not suggest to separate this inter-exchange correlation. But they treated it as the unknown rest, as I said. Another question is, how could you, now if you are left with this and you have no clue how this can look like, do you have an idea what one could do? Okay. So you know this exists, you know you have this, but you would like, in order to approximate the purpose, you would like to look at it. How does it look like, or what can it be? So one thing which one can do is one could say, well, perhaps in some special cases, we know what this here is. If in some special cases, we can calculate this exactly. Imagine you knew for some particular case, you knew exactly what the density, what the exact energy is. Then you can write down what is our TS, you can write down this, you can write down this, and then you know what this is, because it is precisely the difference between the exact one and the other. So what Kronberg and Kohn have suggested is to look at a particular system where one can, not analytically, but where one can calculate on a computer the exact answer. And that is the so-called homogeneous electron gas. So the key to the success of these approximations is to look at something which is called homogeneous electron gas. Sometimes it's also called homogeneous electron liquid. It depends on what the density is. High density or low density, it's either the homogeneous electron gas, homogeneous electron liquid, and it's approximate HEG or homogeneous electron liquid. What is it? Well, it is simply, it's a very easy concept. It is what electrons would do if there were no atoms which act on them and force them to be in a given region in space. Okay? It is the case where you have an infinite space, you put in electrons, and there is no structure to the electrons, it's everywhere, it's homogeneous, it's everywhere in space the same charge density. Okay? So it's homogeneous in the sense that n of r is simply n, independent of r. Of position. So you have an infinite space, you have at every point in space the same charge density. Okay? And then this here is the number of electrons per unit volume. If you multiply it with the volume, we have the total number of electrons you put in the volume. Okay? So you can calculate. So if you have, for example, 1 electron every cubic angstrom, you have a given thing, or while you have, I don't know, 1 electron every cubic meter or so. So you can define various densities, more or less electrons. And the nice thing is, in this case, which is kind of a universal case, because it's independent of if you're looking at a molecule or this element or that, it's only electrons in this space. They have a constant density. There you can calculate the exact energy.
Excuse me, sir.
Yes.
We can't normalize this if we take infinite space.
Yeah, if space is infinite, then the number of electrons is also infinite. But the number of electrons, and obviously the energy is also infinite in that case, but the energy per volume and the number of electrons per volume has a well-defined quantity.
But our real life problem...
When we say it is unit all over space, infinitely large, it is because one does not want to have to deal with some border conditions where it goes to 0 or something. Okay? So we have an infinitely large system. Obviously this means infinitely many electrons if you have a finite density. And obviously this here is also infinite. Yes, but I mean you can calculate everything referred to per unit of volume. And then everything becomes finite. Okay, so you have this. And people can, this is out of the scope of this lesson here, but one can calculate the exact energy of a homogeneous electron gas. Okay? These people calculate the exact energy, exact many fermion energy for a homogeneous electron gas, and this is done with the quantum Monte Carlo methods. quantum Monte Carlo. So it's also obviously an approximate calculation, but it's as one can push the accuracy of this thing as far as one wants. Okay? So it was clear already at that time that the homogeneous electron gas is something which is computationally doable on a computer. So this here gives you the E homogeneous electron gas, not as a functional, but as a function of n. N is now a number, it's not a function of space, this is now a function. Okay? So this here is kind of known as a function, not a functional, as a function of n. Some pioneers of studying the homogeneous electron gas, in fact, are working in this building here. There is a professor at the University of Trieste, his name is Gaetano Senatore, and Gaetano Senatore is one of the famous, or people famous for very fundamental work on homogeneous electron gas. So this is by no way something trivial, because again, if you have, even if you don't have a structure, you still have fermions which interact, there's correlation there, there's all kinds of things there, but it is stuff which can be calculated with stochastic methods on a computer as good as you want. So here we say we do not know at all what this is. But in the special case where n has no structure but is a constant everywhere in space, in that particular case we can get from quantum Monte Carlo this energy here, or this here we can write down, and therefore we know what exchange correlation is. Now I found, proposing this approach, I find it really daring, and it goes beyond my understanding of science, why one had hope that this could work. Because if you look into a molecule, for example, or if you look into a solid, the electron density is not constant at all. You have very high density close to the nucleus. You have very high density close to a chemical bond. Then you have right next to it in the distance of fraction of an angstrom, you have very low density where there is no chemical bond. Then again high density. Then there might be vacuum. So a real system like the ones in a material we are looking at, the density is not at all nearly constant. No, it is changing completely from 0 to a high density on the scale of fractions of angstroms. Okay? So we will be looking at systems, and one is using DFT, in systems which are not at all, from an electronic point of view, constants. So trying to derive an approximation for this here from results you obtain for a system which has the same constant everywhere is, in my opinion, a big step ahead. But obviously, I mean, Walter Kohn especially was such a brave man with such a deep understanding of science. He must have had his reasons to propose that this might be a good approach. And this, as I say, is really the cornerstone of most of modern physics in this area. I should also say, you remember in the first lesson, I have shown you, kind of to motivate you why electronic structure is important, I've shown you a list of papers which are very highly cited by many people. And I don't remember if it's number 1 or number 2 of the most highly cited papers ever published in physics since 18-something, is a paper which is by Sepperley and Alder, David Sepperley and Bernie Alder, two famous scientists. And what they have published is precisely this function here. So the parametrization of how the energy of the homogeneous electron gas looks as a function of the density. This is known as Sepperley-Alder. Sepperley-Alder function or parametrization. So this thing of E homogeneous electron gas of n. They have done this, and since at least in the beginning years of DFT, everyone who was doing DFT always had to say which approximation, even today we say which approximation we use here, but one said based on the approximation by Sepperley and Alder on the results by Sebelier, this became one of the most cited papers of all times in physics. So it's really something important. So one might say, why should anyone study the homogeneous element gas system, which is just constant everywhere in space? But this is so rich that even today there are PhD students, even in this building, who do their PhD on intricate properties of the homogeneous electron gas. I mean, this is really something interesting. So Sebelier, they were amongst the first. In the meantime, many other people have parameterized this function here. But so the important thing for us to know, okay, there is a function. If you know n, even if it's constant in space, then we know what this here is. Simply by really taking the difference between the exact results, Sebelier and Alder, and the other parts of our approximation. Okay, so now we know this, and this has been suggested by them to do. And then comes now what they suggested as an approximation. They suggested to do what is called a local approximation. So this is obviously this. Local density approximation. Known as LDA. So local density approximation, it is, again here everything is important. The word local, you will see why local is so important in this thing. Approximation, because obviously you're approximating exchange correlation. And what you're approximating is the dependence on the density. So now, how did they do it? They said, we approximate this certainly very complicated object by an integral over all space. Then we say the contribution to this energy at a place with high energy will be higher, at a place with low energy will probably be lower. So at every point in space we take the density kind of as a weighting factor. And then we put here a function, epsilon exchange correlation of n at this point in space, and we integrate this over all space. So this is the famous local density approximation. It looks really innocent written like this, no? So the complicated part of the energy is a sum of all points in space on the integral. The higher the density, the more important the point, therefore this weight is put here, in here. This here is now, you see, this is not a function, this is a function of n. Okay? So you plug in here a function of n, and you take as the density at that point in space you're looking at. Okay? Next, you're looking at a different point in space, you will have a different density, and you have a different value of this function. So this is why it's called a local approximation, because you say that this very complicated quantity is something which is a sum over things which happen locally in space. If the density is high, this is high, and you plug in a result from the homogeneous electron gas, which refers to that density locally at that point. Okay? So in order to understand what this means, if you would apply this approximation to the homogeneous electron gas, then it would not be an approximation, then it would be exact. Okay? So this E epsilon exchange correlation, this here is derived from the energy of the homogeneous electron gas, okay, such that the E exchange correlation in the local density approximation is exact in a homogeneous electron gas. Okay, so if you have a system where the density really is constant, imagine you are really applying this approximation to that, okay, then here you have an integral over all points in space, but at every point in space you have the same integral, so it's just the volume times the density times the value of this function for that density which you have. Since you know the energy, you know what this must be. Okay? So you can, in this way, very easily derive, knowing what this here is, you can derive what this thing is. And then You use here the kinetic energy as we have just defined it earlier. You use this, and you take this now for a system where the density varies in space as your approximation. Again, water cone must have had very deep insights, because it is, to me, it looks surprising that something can work. As I said, in a real system like the ones we are looking at, the density is not constant at all. It is not even a constant with some fluctuations on top of it. No, it goes from 0 to something higher, and in no space it is something which has a lot of structure and so on. And we are approximating the crucial part, exchange and correlation. We are approximating it by something where we assume at every point we give it the energy which would be the right one. If everywhere in space it would be like this. Okay? So you go to a point in space where there's a low density, we plug in locally an energy density which would be right if everywhere the density would be so low. We go to another point in space where there's a chemical bond, high density, and we give it an energy density which would be correct if everywhere in space it would be like this. Okay? So it is something which is very well defined. It is clearly a functional. Once you know what this function is, you can calculate given n of r. So this is really a functional of n of r. And this is the celebrated famous local density, LDA, local density approximation. And one can really say, if this did not work surprisingly well, density function theory would probably have been forward, in my opinion. But, so today, few people, or nearly never one, is really still using LDA, and is using some kind of better approximations about which I will be talking. But today's approximations are not so different from this. So this is really the cornerstone of anyone who is doing DFT. The cornerstone is the local density approximations work very well. And because they work so well, and nearly always work even much better than Hartree-Fock, and the calculations are also much faster than Hartree-Fock, because you do not need to evaluate the exchange terms, which is on a computer always very long. This is why people started looking more closely in this, and then the whole area of science has exploded out of this. It is because, miraculously, LDA works really well. We will be talking about the following also when it fails, when it does not work well, but in general, one can say the real biggest success of DFT comes from the big success of this approximation. Now, so I say it works miraculously well. We are scientists, we don't like miracles. And since 1965, many years have passed, okay? And many people have been looking into this miracle, and in fact it's not a miracle at all. But it was only much, much later that it has been understood why this LDA works so well. It does not work so well because the density is nearly constant, as I've said. This is not the case, and this is not the reason. But people later were able to derive a whole series of exact conditions which this functional here must satisfy. Okay? So still today no one knows the exact functional, but knows that it will be something horribly, horribly complicated and non-local and whatever. I know it exists, but it will certainly be very complicated. But people have been able to write a whole series of exact conditions which this functional here, the exact functional, satisfies. So you have a whole hierarchy of more and more, or say, of conditions which this satisfies. And one can show that the LDA satisfies many of the exact conditions which are necessary. And this is the real reason why it is working so well. It is because it is an approximation which satisfies many of the properties which the real one also has. And therefore, well, this is today's understanding why LDA works relatively well. So sometimes there are good news. Sometimes you're in front of a problem which looks like the Mount Everest, a huge problem, and then you try to approximate it with something which seems to be appropriate for a little hill like this, and it works even for the Mount Everest. And this is for me, this was always one of the biggest surprises when I learned all these kind of things, that an approximation which I can write here in one line, which is very easy, and which, once you know about the homogeneous Elkin gas, one can also formulate very easily, that this works so well that this can be the basis for generations of scientists working in this field. So I would like to stop for today with the LDA and keep in mind what we've done. So we know that this exists. Okay? We have put it into little pieces. All of them except these here are universal, kind of. Okay? And we have written for this and that, for these here we knew exactly how to write it. For this here we had to introduce fictitious orbitals. So we will have in the following, we'll work not as E as a function of n, but E as a function of these orbitals. Okay? Therefore, this allowed us to get an expression for the kinetic energy. And then here, which seemed to be the Mount Everest, which will seem to be unsurmountable, we have a very simple approximation based on a homogeneous gas system, and it works well. Okay? I will, in the following, I will explain a little bit what kind of approximation one uses today. So there are many things to make these approximations better. And I've already mentioned, often you hear when you go to a conference and people talk about a given material or given class of molecules, they say, in these transition metal oxides, DFT does not work well. What they mean is the functional one uses is not working well enough. Okay? The approximation for the exchange correlation function. So LDA has a lot of nice properties, it often works well, but there are notoriously important and notoriously difficult systems where LDA does not work good enough. And by today there are many remedies of other approximations or other things. But I will talk a little bit about these things also in the following. But as kind of the cornerstone, keep in mind this very easy form for the very complicated exchange correlation effects. Okay? So this is the way how one gets away with electronic structure theory without dealing with a many-body wave function and without dealing with 10 to the 100 determinants and whatever. Okay? Good. So on Friday we'll continue with these lines. On Friday we will also do some Socrative again. Yes.
Why is it approximation? Can we put that N and S as still
Well, so there is something, since you asked,